Welcome to a high-level course in measure theory. We'll be going over most of the topics that you might cover in an undergraduate course. So before we begin, let's talk about what measure theory actually is and why do we care? So measure theory is basically a formal way of generalizing lengths, areas, and volumes. We work with these functions that we call measures, and they output these generalized areas of subsets of certain sets that we might be interested in. Measure theory is super important when it comes to defining the Lebesgue integral, which is generally seen as a better formulation of integrals over the Riemann integral, which you might learn in first year, as it has quite a few advantages. It's also super useful in foundational probability theory. So to begin our study of measure theory, we first need to look at what subsets we can actually define a measure on. To define a measure on subsets of a set X, we need these collections of subsets to have certain nice properties. And these collections of subsets with these properties we call sigma algebras of X. And these collections are generally denominated by A, and they are subsets of our power set P of X, which is just a set of all subsets of X. Sigma algebras have three properties. The first is that the empty set must be in our sigma algebra. The second is that if we have some set A, so if we look at our set X and we look at some subset A, and that's in our sigma algebra, then its complement is also going to be in our sigma algebra. And the third is that for any collection of countable subsets, so a countable collection of subsets, which we denote with AK, in our sigma algebra, so here we can draw a bunch of subsets. Their union also has to be in our sigma algebra. So this entire bit together, this subset, must also be in our sigma algebra. And this can be for an infinite collection or a finite one. It just has to be countable. We can actually replace property 3 with two other equivalent properties. So the first is that if we have a collection of subsets and we restrict it to be disjoint, then the union has to be in our sigma algebra. And the second is that if we have two sets, A and B, in our sigma algebra, then the intersection also has to be in our sigma algebra. And the way we want to justify this is, let's say we look at our set X here, and then we look at these two sets. By property 3, we know that these two sets have to be in our sigma algebra, or rather, their union has to be in our sigma algebra. So we want to prove the same thing using these equivalent properties instead. So what we can do is we can try to break this down into three disjoint sets. So A without the intersection, and then B without the intersection. And now all we have to do is prove that these are in fact part of our sigma algebra, and that's where this principle 2 comes in. So now all we need to look at is kind of our three sets. So we know that A without A intersect B is the same as A intersect the complement of A intersect B, and since property 2 is saying that any intersects are also in the sigma algebra, this must also be in our sigma algebra. This is the same for B, so B without A intersect B fits the same thing, and then A intersect B is also in our sigma algebra just by property 2. So now let's look at some examples of sigma algebras. So one of them is just the power set of X, and we know that this is a sigma algebra since it contains all possible subsets, so it satisfies all the properties that we possibly need. The second is the most simple sigma algebra that we can have, which is just the set with the empty set and X in it. And we can see that it kind of does satisfy all three properties. So it's just kind of going through these. The complement of the empty set is X, which is in our set. The union of the empty set with X is X. The union of the empty set with itself is the empty set. And we have that the empty set itself is in our sigma algebra. So we've proven property 3, we've proven property 2, and we've proven property 1. So it's a sigma algebra. Some basic results that we get from our definitions of sigma algebras are the following. Since the empty set is in our sigma algebra, then its complement by property 1 also has to be in our sigma algebra. We know that it is closed for countable intersections, and we know that for a set of sigma algebras, and we know that for a collection of sigma algebras, the intersection must also be a sigma algebra. So let's first look at result 2. By basic set theory, we know that the intersection of these sets is the same as the complement of the union of the complements of these sets. Since AK is in our sigma algebra, then its complement must also be in our sigma algebra for all K. and so their union must also be in our sigma algebra. And since the union of these complements is in our sigma algebra, then its complement must also be in our sigma algebra. So we've proven that the intersection of AK must be in our sigma algebra. For result 3, we just need to check if our new set A has the required properties for a sigma algebra. Okay, so property 1 is the empty set in our sigma algebra. Well, we know that since the empty set is in every single one of the sigma algebras in our collection, then the empty set must also be in the intersection of these sigma algebras, which is A. Property 2 is checking whether the complements are also in our sigma algebra. So if we have some subset in A, then it must also be in every single sigma algebra in our collection, so for all I. Therefore, the complement must also be in every single sigma algebra in that collection. And since it's in every single sigma algebra, then it's in the intersection, and so the complement is also in A. Finally, is it closed under union? So if we have a collection of subsets in A, then we know that this collection of subsets will also be in every single sigma algebra. Therefore, their union must also be in every single sigma algebra since they are sigma algebras, so it's closed under union. And thus, it is also in A. And so since we've proven all three properties, we know that A is in fact a sigma algebra.